All right. Can you hear me?
Yep.
Good. How are you doing?
Pretty good. How about you?
Good, thank you. All right, let's start. So we're pretty much done with mechanics and everything. I told you everything which I will need later on. And so now what I'm going to talk about today is about waves, right? And it's very close to mechanics. In fact, a lot of mechanics of like say continuous media is dealing with waves. But I'll talk about it a little bit later. But right now, I just want you to remember what waves are, right? And a lot of things which I will talk about today, you already know, but I just want to establish like common ground and maybe like point out some things which you don't know or didn't pay attention to. So let's remember what kind of waves do you know? Can you say me? Can you tell me? Come on, guys, I need answers.
Wait, what was the question?
What kind of waves do you know? When I say the word wave, what do you have in mind? When I say the word wave?
Like radio waves, sound waves, X-ray.
Light waves.
Yeah, right. Light waves.
Say it again?
He said it. He said light waves.
Yeah, it's those are the same. It's electromagnetic waves, right? X-ray, microwave, radio waves, they all go the same. It's electromagnetic waves. But I mean, come on, why don't you say water, like water wave? Right?
Yeah, that works.
You throw a stone in a pond, right? And there is ripples going through from it. So it is also waves. All of those are waves. And it turns out that they all have common features and they have common description. Their interaction with each other, interaction with some other stuff can be different, but if you try to describe just waves, the description will be more or less the same. Right? It's something which propagates, right, and it's like sort of oscillates, and that's good enough. That's good enough start. And now, first of all, let's be a little bit more precise about it and say that when we talk about waves, we talk about observation of different phenomena, right? The description is very similar, but what we observe is different, right? So when you're observing the ripples on the water, you're observing height of the water, right? It's changing with time and then distance, right? That makes sense? When you're talking about sound waves, what you really need to describe is a pressure. So the pressure is in air, for example. If sound is propagating through air, then the pressure is different. It depends on time, and it's also different in different places. So that pressure waves is exactly what the sound wave. All right, it really is. We hear it as sound, but not always. If it's too frequencies too large or too low, we actually don't hear it, but it's still there. Sorry, and its common description is just how pressure depends on time and distance and coordinate. So that's so we observe the pressure, the difference of pressure between equilibrium pressure. So there is always equilibrium pressure, right? But when I'm talking, it's I produce some I don't know how ripples of that pressure in the air, and those and of course when pressure is changing, it means the concentration of particles is changing. So there's more black particles here, less particles here, more particles, air particles here, and so forth. So they're all connected. There is thermodynamics involved there, and there's plenty of different stuff there. There is like pressure, there's a sound with constant temperature, sound with constant entropy, and so forth. So there are a bunch of different descriptions. They behave somewhat different, depending on the conditions and so forth. But nevertheless, it's still the same. It's just there is common pressure and there is some ripples of the pressure. Now, when that's a sound wave, right? The same thing is the ripples, right? You have a common height of your pond, and there is some ripples of that height in the pond which are propagated. Now, electromagnetics is a little bit different. As there is no common thing, anything. It's a vacuum, right? But then there is electric or magnetic fields which depend on time and on coordinates, and that such situation that they will propagate. Again, we can describe them as a bunch of waves. Such propagation, and that's what we call a little like microwave, X-rays, light, radio waves. They're all the same. It's just different frequencies of the same phenomenon. Gamma rays, same thing. So it's so that's so when you try to do like real physics of system, of course those waves will interact with something else differently, right? Pressure will interact differently from electric field. That's sort of obvious. But when you are talking only about propagation of waves, or that really doesn't matter, we can all describe them with the same machinery. And moreover, it turns out that there are a lot of common features of all waves. In fact, those common features are what defines what the wave is. So right now we have this intuitive description of what something is like, propagated, blah blah blah. But in reality, there should be we should be a little bit more precise there, and to distinguish between beam of particles and the waves, and that there are common features of waves which cannot be ascribed to properties of particles, at least classical particles. In quantum mechanics, we can, and those features are define what waves are. And I'll talk about it a bit later. But now I want to also tell you something which you actually know, but probably not noticed. That a lot of waves are just collective excitations. That's what we call in physics. So again, let's imagine that what I have, what the simple sound wave, right? So I do have air here, right? Here, everywhere. And it has some pressure, and it's equilibrium state, whereas the pressure is constant everywhere, and then there is a theorem in thermodynamics and stat mech that the pressure is constant when it's in equilibrium. But then what I do, I disturb it a little, right? With my, I don't know, vocal cords and whatever the machinery is there producing those sound waves, I disturb that equilibrium. And that disturbance of the equilibrium, or we call it excitation, something which when we have an equilibrium and we excite it, right? We disturb it. That disturbance of the equilibrium actually propagates as that pressure ripples, and that's what we call sound waves, right? And we then describe sound waves. In reality, what is here is just air, molecules like moving around and so forth. But we can that's an equilibrium, right? When I produce sound waves, it's also just molecules moving around. There is if you zoom in, that's the only thing which you see, some molecules moving around, colliding and so forth. But I can, instead of like thinking about molecules, I actually can describe that excitations above equilibrium through some machinery of waves, saying that there are some sound waves propagating in this room, right? Now, if those sound waves are too large, right, so that like I have to move a bunch of molecules around, then of course it is not a weak excitations, right? And then the sound waves, the description would actually not work. Those sound waves will become like shock waves and different phenomena and different instabilities and so forth. But when the disturbance is very small, or we say the excitation is weak, or the excitations of the equilibrium are small, that those excitations are excited in one place, right? I excite, like I take some local space and I increase pressure there somehow. And that increase of pressure will propagate. And that propagation can be described as propagation of some sound wave. So the properties of that air in here, when the energies which I put in are not too large, can be described in effective way as if there is some sound waves propagating everywhere. So in this sense, waves are describing the excited state of above an equilibrium. Remember that equilibrium is always a minimum of potential, right? And potential energy, and then I just excite it, and it starts to oscillate, and those oscillations can be described as waves propagating. So waves and oscillations are very, very, very much connected. It's pretty much the same phenomenon. And that's what I was talking about. And when I say that a lot of physics is just physics of oscillation, because a lot of physics is just the physics of weakly excited states above equilibrium. And so you have equilibrium, you're weakly excited, and then we know that it should be sort of oscillations, but because we now have also time and coordinate, we actually have propagating waves. And that's exactly that kind of physics which I was talking about on oscillations. But it's actually in fact very, very general phenomena, and pretty much for any equilibrium, for any state which we find some state of equilibrium, and in a lot of cases that's that when we disturb that equilibrium a little bit, and that's what we have to do in order to observe it, right? When we disturb an equilibrium a little bit, we actually have we can describe those excitations, the physics of those excitations, as the physics of propagating waves on top of the equilibrium. What kind of waves will it be? What kind of physics they will have? Will depend on, of course, on what kind of system you consider and what is your equilibrium. But waves have very common features which exist no matter what it is. What the wave is, and I will talk about those features a little later. And so, for example, something which you may not thought about: if you have a magnet, right? All that magnetism. What magnet? What does it mean, magnet? You have a bulk material, right? And in every point of that material, on every side of the crystal lattice, whatever, it depends on how much you zoom into the system. You have a magnetic moment which is pointing to the same direction. Right, so those magnetic moments are pointing to the same direction. This is called ferromagnet, and that's what gives you the total magnetization of your magnet. Right? It's not coming from anywhere, anything else. It's just small magnetic moments which are all aligned on the same in the same direction. So when you look at it, you need on the whole of it, you have the sum of all of those little magnetic moments. Now each of them is small, but its number of them is 10 to 23. So you multiply small by 10 to 23, you got like something measurable. And that's exactly that magnetization of a magnet which we observe. Right? But now let's imagine that I took that magnet and I take some local probe, whatever it is. We do have some different ways to do that. And I change magnetization, direction of magnetization at one point of that magnet. What will happen then after that? Can you imagine?
Sorry, could you repeat the question again, Professor?
So you have a bulk magnet, right? So it means that on every side of the lattice, you have a small vector of magnetization. All vectors are pointing in the same direction. That's called ferromagnet, and that's why magnets are magnetic. Now let me take some probe, and in one point, just one single point of the magnet, I change the direction of magnetization somehow. What will happen next?
Won't it interfere with those next to it?
And
change the magnetic field?
well, there's no magnetic field per se. I mean, it's magnetization. You can describe it as magnetic field, but yeah, well, magnetic field outside will change a little bit, but not too much. So think about it. Energy is conserved. Everything is the same thing, right? So you change magnetization here a little bit. It will, but I do it fast, right? I just take it and I change it fast. So the next one after that will also try to change, but but by doing that, it will drag the other one, the next one, and the next one, and the next one. So what you will see is the following: that I change magnetization at one point, and the wave of magnetization, of change of magnetization, will propagate away from that point. So in this sense, the magnetization will also propagate by waves. Those waves are called magnons, right? Well, magnons, well, let me talk about it. So those waves are typically called magnons, and in fact, a lot of research which I do and which a lot of other people are doing are related to exactly that story. And the story is very interesting because it's a wave, right? It's actually carries some information. I can either put wave or destroy it or do something with it. Just the same as electromagnetic waves, right? They will, those waves of magnetization will propagate, right? And then I can use that as a carrier of information, the same way as electromagnetic waves are used to carry information, right? That's what we hear right now, and the same way those waves of magnetization can be used to carry information, right? And then instead of moving electrons around, which always associated with heat, right? I will move those magnetic waves. There's also some heat involved, but a lot less than for the electrons. And so it means that I will have almost dissipation-less way of transfer information if I can figure out how to do that effectively and what are the best ways to do that and so forth. So we can actually build some computer devices out of those, probably, I mean, presumably. We can build some computer devices based on those magnetic excitations. And then we will not have that problem of overheating of different systems. So that's one of the areas of the research, and it's actually called Spintronics. And what we do expect is actually that will be the future of electronics. Instead of electronics, instead of using electrical currents, we will use something which we call magnetization currents, and they will do the job of electrons. So it is probably coming in like in next, I don't know, 10 years, something like that. By the time you'll be looking for your next job.
Professor, would you repeat what it's called? Magnet.
Okay, I'll talk about this just in a second. The thing is that it's every wave in quantum mechanics corresponds to some particle, and every particle corresponds to a wave. We'll talk about it when we study quantum mechanics a bit, but that's the whole mantra. The waves and particles are the same thing in quantum mechanics. They're just different wave, or different point of view on the same phenomenon. So every wave then can be ascribed to a particle, specific particle. For example, sound waves, the corresponding quantum mechanical particle is called phonon. Electromagnetic waves, the corresponding quantum mechanical particle is called photon. Right? For magnetization waves, the corresponding quantum mechanical particle is called the magnon. Right? And so forth. So, but because magnetization are coming from what is called spin, it's called spintronics. That kind of research in literature. So it's again, it's the way. What I'm trying to say is the waves are a lot more common than you might suspect. It's not just that. Pretty much everything, when it is in equilibrium, if we excite it a little bit, it will become wave of propagation. So there is a bunch of theorems about it. It's quite a beautiful story. But that's and that's coming exactly from what we studied in oscillators. That what we figure out that everything is when you observe equilibrium, it is at the minimum of potential energy, and every minimum of potential energy looks like a parabola. So it is oscillator when you disturb it just a little bit. But now, because it also has coordinates in addition to the time, you instead of just simple oscillator, you actually have propagating waves. And so it means that everything which is in equilibrium, if you disturb it a little bit, it pretty much will be described as that little disturbances, excitations, what we call, will be described as propagating of some wave. Okay, that makes sense. That makes sense.
Yes.
Yeah.
Right. Yes, there was a question coming.
Yeah, I was going to ask, what is the difference between the propagation of a sound wave and of a light wave?
We'll talk about it in more detail later, because there is a huge difference. But if you try to describe it, talk about description, then actually there is no difference. It's let's say this way. There are a lot of differences, but there are a lot of things which are common for all of those, for all the waves. And those things which are common for all the waves, basically it's interference in diffraction, which I'm talking about. That those things are used to define waves. We define waves as something which has those common features, interference and diffraction.
Okay. Thanks.
So that's and in this sense, that sound waves and electromagnetic waves are the same. They all have interference and diffraction, but there are some very, very important differences between those two. Also, so it's but again, because they're common, as they're common features, we can study it once and use it everywhere else, and then see what it means for observables. So in this sense, you see that what there is that mantra of condensed matter physics. That's what I do. Is there a special paper even about it by one of the greatest physicists of the last century and this century. His name is Phil Anderson, and he died recently. And it says the paper was called "More is Different." So the idea is that when you have large system, right, its properties are very, very, very distinct from the properties of what that system is consist of. So that bunch of air here is is the properties of the bunch of air, collective properties of the bunch of air is very different from the properties of a single molecule. And then in this particular situation this particular example is the difference that the body, that the big body can support propagating of sound waves. Single molecules, there is no such thing as sound waves for single molecules, right? It doesn't have that property at all. But when we get them all together, then we have a new kind of excitations, which are sound waves. And the same is pretty much everywhere else. It's the same with the magnet. When you have just one magnetic moment of one atom, well, there is no wave. There is nothing there. But when you get them collectively, then and study their collective behavior, then you have those magnons propagating. So the collective behavior of very simple pieces, whatever it is, can be very, very different from the properties of the piece itself. Moreover, it's in many cases it's actually unpredictable. You cannot predict the collective behavior just studying one single element. You have to study how they interact with each other, and that gives you a completely different story. So that's what we call more is different. When you have a big collection of simple things, they can develop new physics, new phenomena, which we can use or study or marvel at, and so forth. All right, that makes sense.
Yes.
All right, so there is a simple stuff which how we describe waves. The simplest possible way to do that, describe a wave, is just to start with the sine or cosine waves. They're the same, they just change the phase. So we can always write that a wave can be described, the propagation of a wave can be described by amplitude times sine, and then I write omega t minus kx plus phi naught. Right? So now t is my time. This is time. This is coordinate x, right? And I consider just one dimension. So here's one dimension, 1d, right? And this is sort of x. This is my wave. Again, what is that? What is here sitting here? It can be different. It can be depending on what exactly you're studying. It can be electric field, for example, right? Then this is electric field. Then it will be electric field as function of x and time, right? Equal something like that. Or if you study sound wave, it will be pressure or difference between equilibrium and pressure at this point. So and so forth. If it's ripples on the water, then this is height of your surface, right? And so forth. So in this sense, all of them can be described by this way. Now, why this sign? Well, first of all, remember that I was talking about. They typically describe some disturbance from equilibrium, right? And then we know that it should be some sort of oscillator, and the solution of oscillator is a sine, right? So, for example, if I'm sitting in one particular point x, and I'm observing the electric field or pressure. So I'm sitting just one point and I observe what happens exactly at this point, right? Then that kx does not change, and what I have then is omega t plus some constant. But that's exactly the solution for the oscillator, right? That makes sense?
Yeah.
So in this sense, that coming from oscillator, but it's not the only reason for that. The other reason is that a lot of a lot of equations which are describing waves, and we will see some of those equations later on. They're actually linear equations, and then if you have linear equations, you can always use Fourier transform, and for any function, for any wave form, you can use you can split it in harmonics, write it as a Fourier sum of different harmonics, and each of them will have this kind of form. Right. So then we can study propagation of each of them separately and then collect them at the end. That's basically the same story as what you do when you try to analyze an amplifier in electrical engineering, right? So typically when you have an amplifier, you put here. So you have input, you have output, right? And you want to know how output depends on input. And but input can be any function, right? So the input can be any function f of t. So it's kind of difficult to analyze the things when your input is any function whatsoever. But because if your amplifier is linear, right? So it just multiplies everything. Then what you can do is to say that f is the sum of a Fourier components, sine, some frequencies and time, and with some amplitude, right? And then, because it's linear, if you analyze the behavior in this, how each of those harmonics goes through amplifier, you can then collect them back together at the end, and then you know the solution for each function. So in reality, the only thing which you need is to describe the amplifier completely. Is how amplifier is working with one harmonic, with each of the harmonic. How that response for one harmonic, it depends, for example, of the frequency of the harmonic, and so forth. So it's you can split things in harmonics, and the same thing here because of the linear equations. And the linear equations in my language means linear amplifier in that kind of thing. So it's basically exactly the same procedure, and then what it means is that we can think about it as just one harmonic of more complicated functions. So then that will be enough, right? And now let's talk a little bit about the terminology here. Well, first of all, this phi naught, which is here, right? It's arbitrary phase. It's actually not important, right? Because if I consider only one wave, right? If I consider two, it is important, but we'll talk about it later. Simply because you see that time and coordinate here, right? But it's time and coordinate, but time depends on when I turn my watch on, right? And the time which the absolute time, the time which my watch shows right now is different than the time which your watch shows right now, right? Because couple minutes here and there doesn't matter for us, right? So it's so two clocks are not necessarily synchronized. So the time is so what is the start of time? What is t equals 0? It's actually it's in my hands, right? It depends on how I started my clock. The same thing with x, right? I can always shift my system of coordinates, and then x will acquire a shift. So it means that those things depend on me, on the observer, on how I measure time from what point, and from what point I measure distance. And the propagation of waves is definitely does not depend on how I measure. Right? Nothing real, which is real in physics, depends on how I measure. So what kind of assumptions I make. So what it means is that instead of writing this, I can write it like this. Omega t minus phi naught divided by omega naught minus kx. Notice that it's exactly the same expression as the one above, under the sign, right? So if I multiply by omega, if I multiply by omega, then omega will cancel out here, and I get just minus. Here's plus. And I have just plus phi naught, and then that's exactly what it is. But what it means now is that I just shift my time. So what used to be a time 0 now is time phi naught plus omega. So I call this my new time, and it's just a shift when I started when I started my stopwatch. Okay, that makes sense?
Yes.
Or we can do it differently. We can write it as omega t. Then I have minus k x minus phi naught divided by k. Right? It's exactly the same formula as before. But what I did now, I just shifted my x. Right? That makes sense? So now if I call this x my new coordinate, and it's just the same coordinate, just shifted. Right? And then what I will have is the same expression but without phi. So that phi naught by itself is not really important. It must not appear anywhere in our final results. But whatever we are computing, it must. So for example, we compute propagation from point A of wave from point A from point to point B, of how they interact with each other, and so forth. That phi naught must not appear in the final answer because it's not a well-defined quantity. Right? I can always add any constant here, and just and then delete it by just subtract, just shifting my 0 of time. That makes sense?
Yes.
I want to point out here that it's exactly the same as the potential energy. Right? The potential energy is defined up to a constant. I can always take a potential energy and add any arbitrary constant to it. Any. All right? And all the answers must be the same at the end. Because nothing can depend on that constant. Simply because the only thing which actually matters is force, and force is a derivative of potential energy, right? So that constant will always cancel out of all equations of motion. And the final answer must not depend and will never depend on that arbitrary constant, which you can add to the potential energy. And if you don't have such feature in your solution, that somehow your potential energy, adding a constant to potential energy completely changes everything, then what you did was wrong. Simple and clear. It's a very common mistake when students, for some reason, which completely escapes me, think that conservation of energy means that potential energy equals kinetic energy. This is wrong, absolutely wrong. Okay? Exactly for that reason. Because potential energy is not well-defined quantity. I can always add a number to it. And then that equation makes no sense whatsoever. Kinetic energy, by the way, is not also very well defined. Simply because if I measure kinetic energy in a moving frame, then it will be different. So none of those things, neither kinetic energy nor potential energy, is very well defined. They have some arbitrariness. And so they cannot be equal to each other. That makes sense?
Yeah, that makes sense.
The conservation of energy means that the total energy does not depend on time. That's what the word conservation means. Right? And so something total energy does not depend on time. So if you write it this way, saying that initial total energy must be equal to final total energy, then if your total energy is kinetic plus potential energy, so if you now add any constant to the potential energy, you will add the same constant to the left-hand side of your equation and right-hand side of your equation. So it will cancel out. And the answer, the final answer, will not depend on that one. So that's one of the checks which you can do. In reality, this is what I'm describing here is called. It has a name, and we will talk about it a little later in more details. But it's the name is gauge invariance, and this is the most powerful tool in theoretical physics. All of that standard model, all of our description of quarks, we don't know if you heard about it, gluons, quarks, mesons, whatever, they're all based on that symmetry, on the fact that there are special symmetry, which is called gauge symmetry. And this is one of the realization of that gauge symmetry. That gauge symmetry is actually so powerful that it allows us to make a lot of predictions. So it is not a simple story. It's not a trivial point. In fact, it is trivial here, but it's if you try to understand what it actually means, it becomes quite a powerful tool. All right. So what's inside here? So let me then delete that phi naught and write it like this for now. So it's so what's inside sign is typically called the phase. This is phase. Now again, as if I add here phi naught, the total is also called phase, and phi naught is also called phase. So what phase means in any particular situation depends on the context of what is described. But I mean, it's usually clear. If it's not clear, you should ask questions. Now, what is here, what is in front of that sign is called amplitude. Right? So it's sign is going from -1 to +1. So the total wave goes from plus A to minus A, and so it's a maximum, which is that amplitude, the maximum which the wave can have, and it's called amplitude of the wave. All right, now this omega is called frequency. Right? In physics world, when you hear frequencies, that's what we mean. There is another frequency which engineers typically use, which is f, and it's simply that's always forget which one is that. It's omega divided by 2 pi. That's all. There's nothing, no difference between the other difference between them. But sometimes for engineering, especially purposes, it's easier to use f. For physics, it's easier to use omega just simply because in this case, when I use omega, I don't have to carry 2 pi with me all the time. And one of the source of mistakes is forgetting to write 2 pi. And I actually once failed an exam because of that. I forgot to write 2 pi at some point, and it was squared later on in the calculation. So it was 2 pi squared, which I missed. And 2 pi is about 6. 2 pi squared is about 40. 40 is too big a number. And so my teacher said that the mistake is too big. And I failed it, which was a very important exam in my life. But anyway. So the less things you need to carry out with you, the better it is for the calculation. So in physics world, we typically we use omega just to have like those 2 pi's under control. All right. So the units now, everything which is under sign must be unitless. It must be just a number. There is no such thing as a sign of 1 meter, or sign of 1 kilogram, or sign of 1 second. It does not exist. Right? Such an operation does not exist. So whatever is under that sign or cosine or exponent or logarithm, whatever, it must be unitless. Always. If you have something which has units under sign, it means that you made a mistake. That's it. That's the only thing which it can make. Can mean. And it doesn't mean that there is some other way which somebody else knows how to deal with it. No, it's a mistake. That's it. So because it must be unitless, and time, if we count it in seconds, then omega must have units. Let's call it that square brackets here means that it's units of omega. It's just second minus 1, right? It's 1 over second. If you measure time in minutes, then it's 1 over minute. So it's actually the standard situation, the standard universal result is that omega has the units of inverse time. Okay, that makes sense. If you look at this, it has the same units because 2 pi is just a number. It doesn't change units, right? It has no units. So f, the units of f is also 1 over time. Now, because it's used quite commonly in many situations, then instead of that unit 1 over second, exactly second, that unit has a name in hertz. Its name is 1 hertz. So sometimes for f we use in physics we use either units second minus 1 of hertz. Actually, we very rarely use this one. But hertz are never used for omega, right? So if somebody wrote the frequency is like 60 hertz, then we know that it's not omega itself. But not always. So it's that's how units are, right? Now that's about omega. Now there's another thing which is called k, right? This one. We call it wave number. And as again, as k times x is the length, all right. So k times x must be unitless. So it's unit for k is meter minus 1, all right, or centimeter minus 1. Actually, when people do an experiment in electromagnetism, they usually use centimeter, inverse centimeter, but it's just a tradition. In any case, this is inverse unit of length. Okay, that makes sense.
Professor, sorry, what does K stand for again?
It's called wave number.
Okay.
Okay. So or it can be called K thingy. I don't really care how you call things. Right? I care what they mean. And so let's discuss then what is the meaning of those things. So far, it's just like some omega frequency, just words. Meaning means something which you can measure. If I measure something, what I will see, how those things connect with something which I can measure. So let's start with omega, and let's then assume the following situation: that there is a wave right here, like water wave, whatever, and you are just observing one point. So you don't actually know anything about the wave. You're just observing one point of space. So that x naught then is a fixed number. And what you're observing, like let's say you're observing height of the surface, or the pressure, or electric field. What you're observing is at this particular moment of time, right? It's just something which depends on time, right? That is, a pressure depends on time at this particular moment of space. You don't know anything else, but you're observing just one point of space, and you measure, say, electric field at this space, or at this point of space, or you measure pressure at this point of space, or height of that surface at this point of space. So what you will see is something which depends on time. This is fixed, but this still depends on time, right? So if you observe it, so you observe that I don't know, pressure at time t. This is sound wave, and then what you notice, then if I add, so if I observe it in a later time, t plus a later time, which is 2 pi divided by omega, right? Then what will I see? I see here the value is a times sine omega t plus k x naught, right? This is just a constant. That is the value of the wave at time t, and the value of the wave at this point is a times sine omega t plus 2 pi divided by omega plus minus kx naught. So that's what we like observe at this point of time. Right? That makes sense?
Yes.
But now I take this omega and multiply it with what's inside. And what will I have is omega t plus 2 pi. Right? But 2 pi is a period of my function. Sine. So it means that I can take it out. Sine of anything plus 2 pi equals that sine of the same of that anything. So what I have is exactly the same magnitude of whatever I'm measuring. Right? So it means that after this time, the story will repeat itself. So such interval of time when the story is repeating itself is called period. And this is simply period of oscillation of that thing which I'm measuring here as function of time. So connected with that, it means that the period, let me write it here. Period equals 2 pi divided by omega. Right? Or using this one, it also equals to 1 over m. So that's the period of oscillation in time. Now, I really want you to understand that it's quite important that what I did is just I took one specific point, x naught, and I made an observation only at this specific point. Right? And then when I observe at this specific point, I have oscillation with this particular period. Does that make sense?
Yes.
All right. Now, let's do the different experiment. Let's take a picture of our wave at some particular moment of time. So now I fix time to be t0. One particular point of time, let's say I have the ripples on the water, right? And I take a camera and I made a picture. So I see that wave at this particular moment of time. Then I do exactly the same trick. I see that at some particular x, some particular coordinate at this moment of time, what I have is a times sine omega t naught, right? At this particular moment of time, minus k. Well, let's call this kx. This is my at point x at this particular moment of time. Now I took another point in space, which is x plus k plus 2 pi divided by k. Okay. So then what I will measure is a times sine omega t naught minus, now instead of x I need to substitute this, k times x plus 2 pi divided by k. Okay, that makes sense? Now I open it up again, and what I see here is kx minus 2 pi. But 2 pi is a period of sine. So that 2 pi doesn't matter. Give me the same number. So what I have is exactly the same value of whatever I'm measuring, say pressure. So at one particular moment of time, I took the picture of my wave, and I see that the wave repeats itself after that length. Okay, so this length then is called wavelength, and so it's given by 2 pi divided by 2. Okay. That makes sense?
Yep, that makes sense.
So again, for any time, if I measure at some particular point for any time which is t plus any number times period, any integer number times period, I will have exactly the same value. It repeats itself all the time, right? In some particular space point. Now, at some particular time point, some particular moment of time, the wave repeats itself at each point x plus n times lambda. And again, n is any integer, right? So it's the same picture. It's always the same. So that's this way. That makes sense?
Yes, yeah.
Okay, good. So I again, at some particular moment of time, right, what I will have, this is x. Now it's only function of x. This is my wave, and what I will have is something like this. Well, it doesn't start with 0. It's something like this, right? And the wavelength is exactly the length, the real length of this wave, of this side. So this is lambda. That is. Right? Now this is at some particular point time naught, t naught. At some particular point of space x naught, I can measure the values of the pressure as function of time. So now this is my time, and this is wave. And I again have exactly the same, well, I have the same kind of function, right? And now this time, which it takes to go from here to here, for example, is exactly the period. It's also the same time period between this point and this point, right? Or between this point and this point, and so forth. So it doesn't really matter. The story repeats itself after every period. And the same with here. So you can measure lambda between this point and this point. You can also measure lambda between this point and this point, the wavelength. It's the same length. The story repeats itself along the coordinate axis. Okay, that makes sense?
Yes.
Okay. Now let's now do a third experiment. And so we know now that the wavelength lambda equals 2 pi divided by omega, and sorry, it's period. And wavelength equals 2 pi divided by k. You see that they're very, very similar to each other, right? So now what we have, we do this third experiment. We just look at the wave. We are looking at the wave, right? We're just sitting there on a beach, right, or whatever, on like shore of a pond, and then we see that waves propagate. Right? So what we will see? Let's say that we have a wave at some point of time, and this is the wave, right? And what you and what you see, that's at some point of time, you know. And we notice the position of this. I think it's called crest, right? Right? How do you?
Yes.
Yeah. Okay. So we notice the position of this crest. And that what do you see? Like, just remember, you've done that experiment, I bet, many times. If you haven't, go to your bathroom and do it. And so what you will see is that your the crest is moving, right? Right?
Yeah. Mhm.
So now, after time t, this crest will be here. Because it must repeat itself. The picture must repeat itself after time t. So it means that wave is just moved exactly here. So it takes time t, capital T, the period. Right? For the crest to move from here to here.
Yes.
On the other hand, if you look at just at one point of time, then you know that this length in x is lambda. Right? So during time t period, capital T, the wave moved the distance lambda. So the wave, the speed of wave, the velocity of wave is a distance lambda divided by the time it took that wave to travel that distance, which is capital T. Right? That makes sense?
Yes.
Now, using the other things, you can also write it by saying that this is lambda times f, right? Because t is also equals this is 1 over f, right? So this is 1 over f. So I substitute here, I get lambda times f. That's the same expression that's in here. It's a sign of equivalence. It means that it's just the same expression written differently. Or you can write it using those formulas. Then the same velocity sorry, is omega divided by k. Right? So when you know omega and when you know k, you actually know how that thing is propagating. What velocity is propagating. Does that make sense?
Yes.
Another good thing about it is that if you know that the velocity of your wave is a constant, it's not necessarily constant. But if you know that the velocity is constant, it means that it does not depend on omega, for example, on frequency. Like sound waves, when frequency is not too large or not too small, that velocity of the sound waves is a constant. And then you actually know how omega, so you know this constant, you can measure it. And then there is a specific connection between omega and k, right? If the velocity is a constant. The same as for the electromagnetic wave. We know that they're moving with the speed of light, and it means that the omega and k are connected, and c is the speed of light, which is universal constant. So the frequency of electromagnetic wave is always velocity times speed of light times wave number, and wave number is given by lambda, right? So the wavelength. So in particular here, what you see is that the frequency equals this frequency equals c divided by lambda, right? So if c is the speed of light, then you divide it by the wavelength, and you know the frequency. They're strictly connected with each other, right? If you know one, you know another. If you know frequency, you know electromagnetic, you know wavelength. That's why you call like microwaves. Microwaves referring to the wavelengths, right? Actually, don't know what the wavelength. But you also can use this expression and find out what's the frequency of those waves. Okay, and that's why the frequency of the waves, electromagnetic waves, are very often in radio, right? Are measured instead of giving you the frequencies, they give you wavelength, like a centimeter wave or 10 centimeter wave or meter wave, right? Right? For electromagnetic waves, you've seen this, right?
Yes, yeah.
But simply because if you know the wavelengths, you can always compute what is the frequency. Just take the speed of light, which is known, right, divided by wavelengths, and that's it. You're done. It's the frequency of the wave. So if you know if your wave is simple enough to have that property, you can always do that. And but it's not necessarily so. There are some waves where you have omega frequency of those waves. Some functions sometimes quite complicated of a wave number. So here it's very simple, right? That omega, according to this, right? That omega equals c times k, right? Where c is just known number. For example, for light is the speed of light. For sound, it's the speed of sound, and so forth. But you see that this is how omega depends on k. Now this function can be more complicated than that, right? It can be, I don't know, k squared for some, but that will not be electromagnetic waves. That will not be sound waves. It's some sort of waves. They do exist, and for example, there's that waves in ferromagnet. They actually have k squared here, and so they don't have actually like established velocity. Right? Every time you need to velocity, the velocity will depend on frequency in some sense. Right? That's what it means. And so it's an omega as function of k, which is which describes that wave, for that particular wave. And this is called dispersion relation. And that's the same. It's the same name as how energy depends on momentum. Because surprisingly enough, this is exactly the same thing. This is kinetic energy, how kinetic energy depends on momentum. This is how frequency depends on wave number. They have the same name. It's called dispersion relation. And because it turns out that wave number is actually nothing but momentum in quantum mechanics, and frequency is nothing but kinetic energy in quantum mechanics. That's how the establishment between quantum mechanics and classical and the particles, quantum waves and quantum particles are established by this dispersion relation. So they have, and that's the origin why this thing is called dispersion relation, because this is actually dispersion relations come from optics. That's the fact that this is not as simple in any material when you have, for example, glass. There is relation between wave number and frequency is not that simple. It's more complicated function, something like that, right? Some function. That's what gives you that prism effect when you have white light and it splits on different colors. All right. Okay. So that's standard terminology. That's standard ways to describe waves. Now I'm again going behind my schedule as usual, and so there are a bunch of effects which you have with waves, and one of those effects are the fact that the majority of cases which we have which describe waves actually linear equations. The linear partial differential equations, we'll see those later. And if the equations are linear, it means that sum of the solution is also a sum, is also a solution, right? So that's the property of linearity. It means that you can take waves and you can sum them up. So, for example, you can have two waves of different frequency. Let's say let's say that two waves have the same amplitude, and so, but one of them is sine omega t plus minus kx, omega 1 minus kx, right? And the other one is sine omega 2t minus kx. Okay, that makes sense? Or let me say that I'm measuring this length in one particular point of space, right? And because it's one particular point of space, this is just a constant, and every such constant can be taken out. So let me just consider a very simple story that I have at one particular point of space, I have two waves which comes there with slightly different frequencies. Right? Now, because of the linearity of my equations, the result is actually just a sum of two waves. Okay, this is not a trivial statement, right? It's a statement of linearity. It is not always so. There is some nonlinear media where it is not so. You cannot just add up things. They start to sort of change each other. But well, simple case, this is just linear equations for waves, and then waves just sum up. And then, like I know that I can use some trigonometric formula to simplify, or not simplify, this equation. So this is actually cosine. And let me now cheat a little. Okay, here. Omega 1 minus omega 2 half times time. And times sine omega 1 plus omega 2 half times time. This is trigonometric expression for just sum of two sines. It can be written this way. Okay? Does that make sense?
Yes.
Now let's now imagine that I have omega 1 and omega 2 are close to each other. So what it means is the difference between omega 1 and omega 2 is much, much smaller than omega 1. So I have, if I have that omega, I have this is 0, I have omega 1 here and omega 2 somewhere here. Right? So the difference between them is very small. So then I can simplify it a little bit. So what I see then is that 2 cosine. Now this is delta omega, difference between omegas, over 2 times t times sine. But now it's omega 1 plus omega 2. Omega 1 very close to omega 2. All right, so omega 1 and plus omega 2 is pretty much 2 omega 1. So what I can write here is just omega 1 t, or omega 2 t. It really, with my accuracy, doesn't. Now what happened? Now let's see what is this? This frequency. This is two waves, right? But this frequency is way too smaller than this one. So it is very slow function times very fast function. So let's now take time and plot first slow function. And it's some I'll explain later why I plotted like this. It's something like this. So one of them is just that function. I shifted a little bit just because you'll see why. And this is my my cosine, right? No, I'm actually wrong. Sorry. It's actually really just like this. Right? And then I need to take the slow function and multiply it by that fast one. Right? The fast one will go like this. Right? So that will be the picture of this function. So I can sort of say that with some abuse of terminology, that this is the amplitude of this function, but the amplitude also slowly changes with time, and so that's what I will have. And those are called beats in sound. If you have two frequencies, that's how you basically tune your guitar, right? If you're what is it, fifth read on top string and the second string should sound exactly the same. And if you put your finger on a fifth right, and plug two strings, if they're not exactly the same, what you will see is just that sound which sort of have beats on it, right? And that's exactly those beats which you hear. What you hear is a difference in frequencies. And so that those beats, boom, boom, boom. And if you tune it closer and closer to each other, the delta omega becomes smaller and smaller. So those beats become I don't know, larger periods and larger. And when those omegas are coincide, then you just don't hear any beats at all. Right? This is just will be zero, right? And cosine is just one. Okay, so that's you actually can hear this effect, and that's what we use in tuning some of the instruments. All right, so that's one story, and with the beats. But there is actually more important story when let's imagine now that I do have the same point of space, so that's just a constant. I have two waves which have the same frequency, but one of those waves, but those waves have different phases. So I have phi1 and I have phi2. Right? So remember, for one wave, the phase doesn't matter because it just like it depends on when I started my time, my watch clock. But for two waves, it does matter, right? Because I can by changing time, I can get rid of this one, but I cannot get rid of both of them. Right? I can only change time once, and the beginning of my time, and then I'll kill phi1, but then something else will left here, phi1 minus phi2. Right? So now using exactly the same formula, what I have now is 2 cosine, and then I have phi1 minus phi2 half, right? Times sine omega t plus phi1 plus phi2. That's exactly the same formula as before for this particular case, right? So you see that the result of the summation depends on the difference of those two phases. So adjusting those differences, right? When phi1 minus phi2 actually equals pi, the difference between those two phases equals pi, then it's pi over 2, cosine of pi over 2 is 0. So those two waves will kill each other. If they have the same phase, then this is 0. So I have cosine of 0, which is 1, and what I have is just twice of the sound of the initial wave, which is of course it should be. Although there is one more thing about it, that typically when we measure, for example, electromagnetic wave, we have some light, right? We are not measuring electric field. We're measuring intensity of the electromagnetic wave. And intensity is proportional to electric field square, right? So when the amplitude increases by a factor of 2, your intensity increases by a factor of 4. So you have a lot more intense light when you have constructive interference. Right? This is called interference of two waves. And when they coincide in phase, it's called constructive interference, right? It requires a factor of 2. But when the difference between phases is pi, then it is destructive interference. And of course, it's sort of clear on the picture, right? The constructive interference is when I just two waves coincide. But destructive interference is one wave is this one, but the other is shifted by pi, right? Shifted by pi is a half of the period, means shifted by half of the period. So what I will have is this situation. And so forth, right? So when I sum them up, I get 0. So this is destructive interference. Okay. Now that interference is very, very important because it's exactly what is this is a property of waves. This only can happen because of that periodicity of the structure of the waves. So when I sum up two waves, even without interaction between them, so I'm just simply summing them up, right? I can get two waves killing each other. You cannot do that with particles. If you have two particles, whatever you do, you have two particles. That's it. But waves, you can. Waves can kill each other. Okay. So that's interference. And now, but it's all in one dimension, right?
Professor,
So
I have a question.
Yes.
So what if two waves have different frequencies and different phases?
Well, then you have beats. Then there is the result will still depend on time and complicated waves. Right. So there is no interference.
Okay, thanks.
Right. So, but you just sum them up and the same as we done before. You got something which is not really something which you can sort of pinpoint. It will be just some formula, some solution. All right. Now, again, well, in the previous result, what I want you really want you to understand is the phase by itself, that phase shift by itself, and that phase here, which I put here, cannot be measured. But the difference between phases of two waves, when I have two waves and I sum them up, right, then difference of phases can be measured. It's called phase shift, and it because it's the result of the sum depends of that phase shift. The interference depends on that phase shift. In fact, when you measure the interference pictures, that's exactly what you measure. You measure the phase shift. All right. This is and again, this is exactly the same as with potential energy. Potential energy itself cannot be measured, but the difference in potential energy can be. It's a well-defined quantity. The same is here, and it's the same origin actually. All right. Now, this is one dimension. So how does it, if we have more than one dimension, let's say 2 or 3 or whatever, so what do they do there? And the good thing to do is to start with like, stones in the pond. And what we know, what we see is that there's waves like that. That's how you usually draw them, right? Those waves. Now, what you draw here is the crest of that waves, right? This is those lines in one dimension, or those points, right? In one dimension, this is just one point. Well, some points here is lines, right? Does it make sense?
Yes.
And so those lines are called wave fronts. Now notice that those lines are lines where is that argument of the sign, right? It now depends on vectors and so forth. So in this case, means that k number becomes k vector instead of r x. We have vector r, and this is a dot product between them. That will be the wave in many dimensions, as many as possible. And so, but for those, all of those wave fronts, right? This equals, I don't know, it's a sign, right? It equals, because it's a maximum, it must be equal pi over 2. What's inside the sign, right? Then it is maximum. Right? That makes sense?
Yes.
Yes.
So a wave front is a line in 2 dimensions. This is line where the phases are the same. The phase, what's inside the sign, the same everywhere on this line. If it's maximum, it's just pi over 2. That's all, everywhere. On this line, it's pi over 2. On this line, it's pi over 2. On this line, it's pi over 2, and so forth. So that wave fronts, which you usually draw when you know, is exactly the lines of a constant phase. So the phase is everywhere the same. And with time, these lines are moving away, right? It means that wave fronts are moving. The points where this what's inside equals to pi over 2 are moving. Because you need to solve equation, right? That omega t minus kr equals pi over 2. That gives you dependence of r on t. Right? So that's exactly the motion of the wavefront. So instead of thinking about it as a motion of just one-dimensional wave, what you have is a motion of wavefront. And then there is a dual picture. And by the way, in 3 dimensions, this is motion of surfaces, right? The wavefront now is a surface like spherical, right? And so those surfaces are moving away. Those are wavefronts, and they're exactly the same. This is the lines or surfaces of the same phase. But now you can do different construction. You can actually, at every point, you can draw a line which is perpendicular to your wavefront. Right? Or in 3 dimensions, this is line which is at every point is perpendicular to the wavefront surface. Right? Do you understand this?
Yes.
And you can do it with the fronts of any shape, right? So if it is so, then that line will be something like this, which is perpendicular here, and everywhere. The wavefront. Okay, that makes sense. Those lines have a name. Do you know this name? Okay, I don't have time to wait for your answers, guys. It's all right. The name for them is rays, right? Because this is light rays. So when a little kid is drawing sun like this, right? Then what that little kid is drawing is that lines which are perpendicular to the wavefronts of electromagnetic waves, and those are called rays. And geometrical optics is actually how those rays behave. But in reality, those rays describe, if you know the picture of rays, you can reconstruct the picture of wavefronts. And then you know those waves, right? That makes sense? In quantum mechanical language, it's actually even more even funnier. This is waves of quantum mechanical waves. And rays are trajectories of particles. That's the interpretation of that picture in quantum mechanics. Okay. So in starting from that thing, you can draw you can find out what is the Snail Law, right? Because Snail Law, this is one ray, this is the other, so you have those wavefronts, and those wavefronts hit another material, they actually start to propagate a little bit differently, so they turn around. And just simply calculating how much time it takes for the wavefront to go from this point to this point, you can actually derive the Snail Law. It's just from the picture of the rays as a wavefront, as describing a wavefront, and so forth. This is a standard textbook example. You can read it there. And there is one more picture of which is called diffraction. And let's say if we have a wave which is trying to squeeze through little opening, right? So the picture which is very helpful in this situation. It's called Huygens picture of propagation of waves. So let's consider a wavefront. Doesn't matter how many dimensions at this particular moment of time. Then what you can think about it, what Huygens told us, is that each point of that wavefront is its own source of the wave. It's like if it's a wavefront of the electromagnetic wave of light. You can think about it as that each point is another point-like source of light. The only requirement is that all those sources are in phase with each other. Then each of them, like say this one, starts to producing another set of wavefronts. And this one will start to producing another set of wavefronts. Right? But these wavefronts will interfere with each other. Wavefronts coming from this point and this point will interfere with each other. And if you do that consistently for all the points of the wavefront, what the resulting picture will be, and that can be computed, that the total propagation of the total wavefront. So you can think about propagation of a wavefront as if it is at each point of time, it's actually a bunch of point-like sources. And then you can describe the propagation of any wavefronts, no matter how complicated it is, in terms of the point-like sources. And that is called green functions theorem and green function picture. In particular, in this situation, if I have some rays coming in, so it means that wavefronts come like that, and eventually I have a wavefront which is right here. Right? And then what happens is that each point of that wavefront is now is a sort of light. So they start to produce that light like this. Each of them, right? And they start to interfere with each other. But I see that there is a wavefront over here. So it means that the ray, in order to draw rays, right, I need to draw a line which is perpendicular to the wavefront. So that's what will happen, right? And it also will have some structure inside. So that's that structure and the fact that the rays of light, it looks like they're bending, right? That's called diffraction, and that's another very, very important distinction of waves. With respect to particles. If I have just a beam of classical particles, they just go through and go as they are, right? So the only thing which with particles will happen is that I just cut them and they inside this opening and they just go like that. While waves actually bend around the corner. And so the classical particles do not bend. By the way, quantum do. Quantum particles behave this way. So they actually do bend a little bit. But that again, that's a huge distinction between waves and classical particles. That's a diffraction, right? All right. So there is a couple of more things which are the same sort of stories of interference, and they called resonances of the waves. And let's now. And it's coming from the following effect. Let's consider two walls and put a sound wave in it. So that sound wave is propagating back and forth, right? But think about it, that when propagating back and forth, it actually interferes with itself, right? And the only wave which interferes positively, like constructively with itself, will survive. The rest of them will go to zero. Will kill each other. So what it means is that for any wave, in order to exist in this resonator, right? So this is half of the wavelength, and the resonator is L, right? Then the condition for that resonance is I have exactly, well, actually L. Sorry, here it's, otherwise it's going. So for example, like look, think about it. That wave goes in, then it kicks out, and then it goes like this way. So it will interfere destructively. So the only way to have that resonator is to say that the total length equals some integer number times the wavelength. Then I have integer number of wavelengths fitting in, and all those waves will interfere constructively. The same thing I can. That's one resonator. The same thing with resonator. Let's imagine that I have a tube, very thin tube with a radius r, and I want to put a wave inside. That wave will start to propagate, right? But unless it comes back here with exactly the same phase as it started from, it will interfere itself to death. So the only waves which will survive in this resonator are such which 2 pi r equals lambda times any integer number, right? So r is a fixed number, so only lambdas which will have this relation, for which those relations is possible, then will survive. That makes sense? So this equation for lambda, right? So only lambda, only those waves which have wavelengths lambda n equals 2 pi r divided by n. Only they can exist in this resonator. The rest will not exist there. They will not fit in. And that one, and now we know lambda, right? So if we know the dispersion, we know wave number, and if we know wave number and we know dispersion relation, we can find out what is the frequency of those waves. For example, does that make sense?
Yes.
All right. There is one more effect which I need to talk about, and I probably will not be able to do it very in many details. It's a Doppler effect for sound. So that's the story. Let's consider that we have a source. This is source, and we have an observer. All right, and the source is producing waves, sound waves, and this is air inside everywhere. The sound waves are propagating, and this observer is observing. Right. So let's just consider that picture without anything. Right. So what happens? That sound waves are producing wave fronts. Let me clean it up a little bit. And I say that there are wave fronts which are produced like this, and that person, that observer is hearing them. Right? That's the story. So the frequency here is f source, and the frequency which observer is observing, we call fo, observer. And in this particular situation, this frequency equals to this one, right? Whatever the sound is, the observer observes. But now let's imagine that this person is moving with velocity v, this source, towards, right? So let's say that at some particular point, that observer, that source produced a wavefront. Right? So after one period, t, right, this wavefront has moved distance, which is speed of sound times the period. Right? So after one period, and that period, that t, right, is a period, is just 1 over fs. Right? So what I have here is that at some particular time, that wavefront which was produced at that particular time moved the distance, which is c divided by fs. At the same right? This is after time period. This during the same time that source move distance, which is v source times the period f s, right? So that wavefront now this is the previous wavefront, and now the wavefront is here. So the distance between the wavefronts, that distance between the wavefronts is c divided by fs minus vs divided by f. This distance minus this distance. Now it is two fronts, right? And they just propagating like this. But the distance between them, between those two fronts, is this one. Right? Does that make sense?
Yes.
So now I look at the observer and I see two wavefronts. So one wavefront is coming, and the next is coming after the time, which is this length between the wavefronts, divided, so this length, divided by the speed of sound. This is the time between two incoming wavefronts. But that time between two incoming wavefronts in one particular point is exactly 1 over frequency. It's a period, like, so it's 1 over frequency. That make sense? So let me invert it now. And what I have is frequency which observer is hearing is equals frequency which the source produces. And then I have c divided by c minus vs. So c is the speed of sound, vs is the velocity of the source, right? And this is frequency of the source, this is frequency of observer. So the frequency which observer hears is different than the frequency which the source produces. And in this particular geometry, you can see that this number is less than c. So that frequency is actually larger, right? So c divided by c minus vc vs is more than 1. So observer actually hears higher sound. Does that make sense?
Yes. And just to be sure, you said c stands for the speed of sound, right?
Well, yeah, right. So the speed of wave, actually. For any wave, that will be correct.
Gotcha. Yes, sir. Thank you.
All right. So if of course if the observer is going the other way, right? So source going the other way, right? This way. Then what will happen? The only thing which will happen, it will be plus sign. And so yes, changes sign. That's all. So in this sense, and then what you will hear is a lower sound. That's of course you can hear, right? And you probably have, and when cars are passing by and with honking, right? You see that when they incoming, the sound is higher than when they outgoing. This is called Doppler effect. Right. Now, what I really want you to understand is the source of the Doppler effect, why it is happening, and it is happening. And this is very, very, very important point about Doppler effect. And I'm sorry that people are leaving because I will refer to it later. It's the fact that there is air. All those velocity Vs are measured with respect to the velocity of the media. All right, so media is where the sound waves are propagating from. And the fact that there is that media means that we can measure all the velocity of the source and observer with respect to that media. So the idea that the Doppler effect only can be explained if there is a media through which the sound is propagated, the wave is propagated. Okay, so it makes you. So, for example, you can do the same calculation, but think that there is a wind, and you will see different result. That wind will occur. All right, that's about it for today, and about it everything which I wanted to say about waves. And any questions?
Does a vacuum count as a medium?
No.
Okay.
That's exactly the point.
Okay, thanks.
All right. All right then. Thank you.